Okay, valley networks. So when Mariner 9 went into orbit, it saw that Mars was a much more interesting planet than we saw from Mariner 4, 6, and 7. Again, what was the view of Mars after the first Mariner missions?
It was basically like
Basically like the moon, dead, cratered, blah, not interesting. Okay, Mariner 9, first orbiter, was greeted at the planet by a global dust storm that prevented it from seeing anything. And then when the dust storm abated, we saw Olympus Mons and the Tharsis Montes, these huge volcanoes. We saw Valles Marineris. But one of the other striking features that was found as far back even as Mariner 9 were these valley networks. Okay, very characteristic structures in some different parts of the planet. And so here we have these striking landforms. So here's just one of those landforms. And so our first step in trying to figure out what's going on here is just to determine what can we actually observe about this new system that we're looking at. So, no interpretations here. What do you see in this image from orbit? Okay, we see some. I'm just going to say there are some linear features. You mean you're talking about like here, here. Okay, what else do we see?
craters.
Okay, we see craters. So, that's not unexpected. We're on Mars, so we see craters. And, if I were going to be a real stickler, I could say we see these circular structures that we interpret to be impact craters. But I'll just take it as given that these are impact craters.
Something like hills or mountains.
Where you
Um,
orient me?
Next to,
Down here? Is that what you're talking about? Yeah. Okay. So we see the dark areas down here. We see lighter areas up here. We would know when the picture was taken what direction the light is coming from. And so we would know that overall we're talking about lighting in this direction. So this dark part represents what? Why is this area dark?
Depth.
What?
Depth.
What, Bertram?
Depth. Atman, light. Air. Depth.
Oh yeah. Okay. There's topographic relief. Difference in elevation. So this would be the shadowed part of this landform. And if the light is coming from this, then which is higher in elevation, here or here? One or two? Okay, so this is higher in elevation. We've got a kind of a cliff face here that's dark in shadow. And let me switch over. So yeah, this would be a cliff face that is in shadow because the light is coming from this direction. Okay. What else do you see? There's a big crater.
the craters.
Yeah. I mean, we don't see a lot of differences in coloration in this black and white in terms of tone or texture. Um,
The linear features, they seem like to be either lower, like the ground is darker around there, and it seems almost like a delta.
okay, so I mean this particular one is shadowed, so clearly that's got to be. Is this linear feature cut into the landscape, or is it mounted up from the landscape?
It's cut in.
Yeah, okay, so these look like they are, I'll just say, incised features. They're cut into the surrounding landscape. What about the orientation of those linear features?
They seem to branch off at the end more, which is, like you said, exactly like a delta.
Okay, so there's clearly some branching going on here. Delta is an interpretation.
Right. Seems like.
That interpretation would indicate what kind of directionality to this branching. I mean, I think of a delta as you've got something coming in and then it branches out, right?
So water will be flowing uphill. essentially.
Well, we're not anywhere near water yet.
Well, right, but I mean, if we're talking about a delta, it's water.
Yeah. Which area do you think is higher? Down here? Down here? Or up here? Sorry. This is actually higher elevation. Up here. And this is lower elevation. So if things naturally are flowing, are not flowing, if things are naturally traveling downhill, then you would have branching, but the branches would be coming together as you go downhill rather than spreading out as you go, in which case would be uphill. So it is a very, what you might call, dendritic or tree-like branching dendritic feature. And so this is, they saw image after image after image of this once they started getting images back from Mariner 9. Okay, so that's the pattern that we see. So we need to come up with what are all of the alternative explanations that we can think of that will allow us to explain those. Aliens. For some reason, they're doing landscape art projects and like Christo, and they're okay. We probably won't pursue that hypothesis much. Okay. We're fairly clear. It looks like that these features are carved into the landscape. Maybe they represent volcanic flows. Lava coming down has carved these channels and is eventually moved its way off outside the field of view of the picture. Yeah.
Some sort of like glacier melting and water flowing down mountain.
So you're actually talking about glacier melting, and so the erosion would be due to liquid water?
Yeah.
Okay.
Those hot springs that like the water just shoots up and then it just starts to flow.
So could geysers be a source of water, which is then going to, what, flow downhill to cut? Okay.
I was thinking glaciers receding.
Yeah, glaciers don't do much erosion when they recede, but they do erosion when they expand. So maybe we're talking about structures cut into the landscape, maybe they are glacial scouring. Channels. And so you might have had lots of different glaciers. They're starting at the top and they're cutting, and as they go down, they eventually join up and they're cutting.
Weather, like rain.
Rain leading to surface runoff. Leading to erosion. So this would be comparable to what on the Earth? I mean, when we have rain falling down and surface runoff leading to erosion, leading to channels that come together, what do we call those?
That's true.
When water falls from the sky and it flows downhill, what does it flow into? Culverts.
Oh,
No.
yeah.
No. Come on, guys, rivers. So, maybe these are river systems. What would the Mississippi River Basin look like if Earth lost its ocean, lost all of its water to space? It would be this dendritically branched structure. Other potential mechanisms that could carve structures into the landscape. We've got lava, we've got water erosion, wind. Generally speaking, we don't see wind carve continent scale structures on the Earth, but Mars is not the Earth, right? Mars has been relatively dry, we know, for a long time. We know the wind blows. If we don't have the continents moving around, we don't have crust being recycled, what would be the impact of wind blowing for billions of years? The wind could clearly create structures that we're not familiar with here on the Earth. So anyway, this is the kind of thing you'd want to do. We've got some new feature we're trying to explain. The best thing to do would be to put everything on the table. What could be all of the potential processes? And I'll just add another one here. Liquefied CO2. On Earth, we're familiar with carbon dioxide as either being frozen as dry ice or vaporizing directly into carbon dioxide gas. But under the right conditions, you can make carbon dioxide into a fluid. And, people had actually proposed that, we know there's carbon dioxide on Mars, so we know Mars is different than the Earth. Maybe these were carved by flows of liquefied carbon dioxide. Well,
What's the 5 say glacial? What?
glacial scouring. So maybe, just the growth of glaciers. And then I need to add one more example of water. And that's groundwater. Maybe flows of groundwater could cut these channels from below in a process that's known as sapping. So water running down over the surface, these are all these and this are examples of surface flows of water cutting these channels. We know on Earth that groundwater can cut out channels as well. I won't go through eliminating all of these, but essentially the two proposals that really have any support at all are groundwater sapping, having the channels cut out from below by the action of groundwater, or basically rain. So, to some extent, understanding the valley networks is essentially asking the question, did it ever rain on Mars? And why would we find that question compelling? Yeah.
If it rained on Mars, that means that, one, the temperature must be high enough that water would evaporate.
Yep.
Also that there was water there in the first place.
Stop. Thank you. Yeah, so nothing much better than rainfall to make a planet Earth-like, right? Moon is not at all like the Earth. We can't imagine there was ever rain on the moon. But, if in the past Mars had an Earth-like hydrological cycle, we would expect there to have been rain. If Mars never was warm enough to have a hydrological cycle, maybe these were cut by groundwater. So that's the big question that we'll address at the beginning next time. So I just want a little writing from you guys to kind of tie up the geology section. And if you want to use your notes, that's fine too.
Oh. Okay, change it.
Okay. Record. I want to just take up where we left off a little bit. Okay. So, to some extent, what we see on Mars kind of reminds us of what we see with river systems on the Earth. That's the whole idea for why these were so generated so much excitement when we saw these first under Mariner 9. So again, we're talking about a branched set of channels where these channels all come together as the channels flow downstream, and eventually, in this case, dump the water that's being carried through these channels into the ocean. I don't think we have to spend a lot of time talking about the different fluvial or river processes. This is middle school earth sciences kind of stuff. Clearly, we've got water cycle on the Earth driven principally by evaporation from the oceans, as well as other sources. That water vapor condenses, falls widely on the landscape, and it's the structure of the landscape that channels the water flowing across the surface into these channels, which then coalesce into, larger and larger river channels as you go downstream. So nothing too complicated here. Groundwater sapping you probably have less familiarity with. This is a process that's present in a variety of locations on Earth that also produce these kind of channel structures, but in this case it involves groundwater eating out or eroding the channel from below rather than surface runoff. So that's really the big difference here. We tend to see groundwater sapping occurring mostly in drier climates, in areas where there's not as much precipitation leading to surface runoff, but you still have underground water, an underground water table. And the other big difference with groundwater sapping is that rather than the channels kind of being created across the landscape and then coming together as the water flows downhill, groundwater sapping tends to build the channels in reverse. There is some kind of cliff face here where we've got groundwater coming out as it reaches that cliff face, and as it does so, it kind of eats away at the rock surrounding the area where it is coming out of the side of the hill. And what that produces is water exiting the hillside further and further up. So the groundwater sapping will basically eat away from what you might consider the mouth of the channel, and these channels gradually eat their way up through the surrounding landscape rather than it all kind of just coming down and being eroded downstream. Which is why these tend to be more stunted and stubby. They're not as finely branched as what you would see with, say, the Mississippi River system with all of its tributaries and so forth, because again, the erosion begins at some downstream point and will work its way back up based on weaknesses in the rock. Every now and then you might get branches coming off, but because it's really, the erosion is really focused at where the channel is being cut back further and further into the rock, as opposed to the erosion being across the whole rivershed, you tend to find these systems being much less branched, stubby looking, and quite a bit different in their appearance to river systems. And this just shows the mechanism again, but I kind of already went through this. So again, it's a matter of erosion taking place at the downstream end, eating its way back up the slope, and therefore cutting that channel headward. And just more pictures of the same thing. So we've got two competing mechanisms. Do these look more like river channel systems or groundwater sapping?
River channel systems.
Some people said these look more like river channel systems. Others said, well, let me look at this one over here. This one this Nergal vallis here doesn't look very branched, right? This one maybe looks a little bit more branched, but there's a big debate. And these are both reasonable mechanisms to explain these morphologies, these structures on the surface of Mars. If you look, though, quantitatively, so once the Viking mission sent back pictures from orbit, researchers could map out the observed channels. They could count up the number of branches. They could measure how extensively branched those systems were. And they could compare it to systems on the Earth. They could compare it to groundwater sapping systems on the Earth. And they could compare it to river systems on the Earth. And based on the initial data, the data from the early missions, say Mariner 9 and the Viking orbiters, looking at the images from orbit there, the general consensus was these systems are a lot stubbier than the Earth, than what we see on the Earth. And therefore, it's more likely that the result of groundwater sapping, and therefore no evidence of surface runoff leading to erosion carving river channels. So let me stop here and ask, what difference does it make whether this is groundwater sapping versus overland surface erosion creating these channels?
Groundwater could mean that it's not very warm and not very good for life.
Yeah.
It's just-
If these are cut by groundwater sapping, we don't even know that there's a thick atmosphere, because you can have groundwater, working underground even if we've got a thin, cold atmosphere. So basically the question is, looking at these systems, do we ever have any evidence of rainfall on early Mars? Did it ever rain on Mars? Maybe that's a bit more poetic way of framing the question, but I think there's nothing makes a planet seem more Earth-like than if you could say, yeah, early in its history there was rainfall, because we don't have any rainfall on the Moon, we don't have any rainfall on Venus. So did it ever rain on Mars is essentially the question that the analysis of these systems really allows us to get at. So the point I want us to go through some more recent work, and I want to do it for two reasons. One is just to answer that question about did it ever rain on Mars, but also I want you to focus on how improvements improvements in our instrumentation allow us to look at these questions at a deeper level and to come up with a clearer, more sophisticated answer. Sebastian.
I was just going to ask, I know it's kind of a little bit off, but do we know of any planets that have ever had rain aside from Earth?
There is another world in our solar system that has rainfall, and that's the moon Titan around Saturn, but it's not water that's raining out of the sky. It's liquid methane and ethane. That sounds wonderful. It's so much colder that on Titan, water is the bedrock, and the liquid that rains out of the sky and cuts channels and flows into lakes and seas is essentially natural gas. Natural gas is liquefied under those temperatures, and that's what's causing the erosion. But it results in a world that looks very Earth-like, because you've got river channels, and you've got coastlines, and you've got lakes and mountains and so forth. But the mountains are ice or water ice, and the liquid is methane.
So there is a lot of water on that moon, but it's all frozen?
Yeah. At least the surface water is all frozen. We don't know if you go down deep enough, do you get to a place where the temperatures are warmer, and you might have a subsurface ocean of water. But on the surface, the water is literally rock hard because of the cold temperatures.
On Titan is, I'm sorry, we're talking about Titan now, but are there like methane like oceans? Like, is it like a vast amount of methane?
Oceans, more like Great Lakes, okay? And it's unclear whether the amount of lakes that we're seeing currently, because currently we've got the Cassini orbiter going around Saturn and periodically going past Titan. And we see a fair amount of lake development currently in the northern hemisphere on Titan, but we don't know if that's just an ephemeral situation. We don't know if that's the long-term situation, because it looks like the lakes are less extensive now than they were earlier in the Cassini mission. Like, there might be some cycles where the climate gets wetter and then drier, if you consider liquid natural gas as wet. Cool stuff. I mean, there's lots of interesting worlds, even in our solar system.
I have one more question. Are the properties of the liquid methane like water? Is it like thicker?
Yeah. You mean the actual viscosity? I'm not sure how the viscosity would compare. I mean, it's going to be fairly low viscosity fluids like water flowing, but dissolved in the methane/ethane lakes, you might have a higher molecular weight petrochemical sludge that would also be part of that system, which clearly would be thicker and gooier and so forth. Okay, so again, the basic question, we go back to this QMRI kind of format, the basic question of this paper is, what is the mechanism for the valley networks? Is it surface runoff or sapping? And again, the previous work had kind of argued for sapping rather than groundwater because of the observed properties of these valley networks. Less branched than what we see on the Earth and so forth. But with the Mars Global Surveyor mission, where we have a much better camera, the Mars Orbiter Camera, the MOC instrument, and especially the MOLA instrument that's doing the laser altimeter, we get much better data on the topography. We can have higher resolution images. We can plot those we can lay those higher resolution images onto an actual digital model of the terrain, the topography, which gives us a much better way of identifying and mapping out and quantifying what these valley network systems really would look like, rather than dealing with a relatively low resolution image from the Voyager and Mariner missions, which were 20, 30 years ago. Well, 30 to 40 years ago now. So for example, here is a valley network system that would have been plotted based on the imagery from the earlier Viking missions. And I mean, does this look very branched? No, it looks stubby. It looks like it could very easily have been produced by groundwater sapping. And this was the kind of results that kind of tipped the balance of the argument toward groundwater sapping as opposed to surface runoff. Here's another area of Viking imagery. You can see individual channels here. There's a little bit of branching there. There might be just a little bit of branching on this one and so forth. But, generally speaking, it looks much more like what we would see out in the desert Southwest from groundwater. But with, and here I think I'm going to have to cut the lights a little bit so you can see this. With the higher resolution images and the digital terrain models, we can see that the earlier images were basically just missing a lot of the fine scale branching that were really present in these valley network systems. So the yellow may not show up very well on the Mars Global Surveyor image, but you can see this is the same valley system. It's the same valley network system with better data. Does it look like they're much more branched if you actually are, yeah, okay, so I don't need to belabor that point maybe. Here's just another one. What they found in this case was what looked to be like independent valley network, stubby valley network systems were actually just pieces of a much larger, much more fully branched, much more mature drainage system. Once you,
Sort of like the rapids of the.
yeah, or these channels were these parts of the channels were obvious enough to pick up with the earlier, less high resolution cameras on the Viking mission. But when you get better data, where you get a higher resolution image, you can see that these individual systems here are really parts of a larger, highly branched system. And quantify that. Well, here's just another case. The Viking image over here, the Mars Global Surveyor image and analysis over here. The other thing with the MOLA data, now that we can measure elevations on Mars to, centimeter scale, we can show that these drainage systems follow the topography. So again, here the white areas are high elevation. You would expect if this was due to to surface runoff causing erosion, that the headwaters of these channels would be at the high elevation sites and they would flow downstream, which indeed they do. Okay. So just to beat a dead horse, this really just shows that as our instrumentation improves, as the quality of our data improves, we can do much better analysis of whatever situation we're looking at. And I won't go through all these numbers, but the authors essentially quantified how branched they were and showed that with the higher quality data, the valley network systems indeed were significantly higher, more fully branched, had higher stream order number. This is, how many sets of tributaries do you go through when you go from downstream up to the headwaters? And, these revised figures based on the higher quality data show that the valley network systems here on Mars really kind of approach the level of branching and stream order that we would see with river valley systems here on the Earth. Okay. So conclusions. Basically, this has swung the pendulum back away from groundwater sapping to more of an emphasis on surface erosion leading to a river-like system. And again, the importance of this is that it really you can't really have this dispersed groundwater or surface runoff unless there is actually some kind of precipitation. We don't know if it was rain or if it was snow that then melted and ran down the surface, but clearly there's some kind of precipitation that was driving this. Okay. So again, the valley networks are principally in the older southern highlands, which means what about when they occurred? Long time ago. So again, we're talking early Mars. Yeah, I don't want to go into this in great detail, but in addition to the valley network systems, we see examples like these green spots here would be examples of what looked like ancient lake basins. Those are also primarily in the southern highlands. And so we're getting this idea built up that if we look at this really old terrain on Mars that was laid down early in Mars's history, we see what looked to be like dried up river systems, what looked to be like dried up lakes. So what's the impression of Mars that we're getting from this?
That Mars had water for a
Okay.
brief period and it's older.
Like early Mars, yep. So again, most of these are Noachian. We will skip over the calculus, but the researchers could ask, well, is just the result of some flash flood event kind of thing, or did these build up over long periods of time? And again, I won't go through the calculus, but they're talking about it taking 100,000 to 10 million years to form this valley network system based on the rates that surface erosion would have taken place. And here, 10,000 to 1,000,000 years for this valley network system to have been created. So that's indicating that these were not just episodic brief pulses of water that washed across the surface of Mars, but are again an indication that there was an Earth-like water cycle for extended periods of time.